Welcome in everyone. In this video, we are going to be covering systems of equations and the three ways we solve systems of equations. So with systems of linear equations, we have two lines, and what we are looking to solve is where the lines intersect, and specifically if they intersect. Okay, so we're looking to see where our two lines intersect, and we all know that lines intersect at a point, so many times our solution is going to be given as a point, an x value and a y value for the coordinates of the point where two lines would intersect. So with systems of linear equations, we have three methods of solving, as well as three types of solutions. So our three methods of solving are going to be substitution, where we plug in one equation into the other. With elimination, we are going to look to cancel out or eliminate one variable, and then we'll solve from there. Graphing, we're going to graph both of the linear equations like we would with graphing lines and see where they intersect, if they intersect at all. Okay, so with our three types of solutions, we have the most common one is where we have one solution, and that's going to be where we have two lines that intersect at a particular point. We may have no solutions where we have two lines that are parallel to each other. And the definition of parallel means that neither line would intersect the other. They run parallel to each other. And then our last scenario would be our infinite solutions. And that's going to be, let's say we graph one line, and then we go to graph our second equation, and it ends up being the same line, meaning that those two equations, when graphed, intersect each other an infinite number of times, going on forever. Okay, and then just to reiterate, when we have one solution, we want to find that point, and our solution is going to be the point with the coordinates of where those two lines intersect. So let's first look at solving by substitution. So the whole point of substitution is I want to have one of my equations with either y equals or x equals. That way I can plug in whatever y is equal to or what x is equal to into the other equation. Okay, so a lot of times if we're just giving out one equation as y equals, we're going to take whatever y is equal to and plug it in for y in the other equation. So if I look at the practice problem we have here, I've got 5x plus y is equal to negative 7, and 6x minus 4y is equal to negative 24. I don't have either equation in a format where it's just one variable equal to an expression. So what we're going to have to do is we're going to have to manipulate one of our equations to make it to where one of our variables is isolated on one side of the equal sign. So if I look at this top equation, I have 5x plus y is equal to negative 7. I already have one y here. Okay, it's primarily alone, but it has this 5x hanging out with it on this side of the equal sign. So I'm going to manipulate this equation to where y is isolated. So if I look at 5x plus y is equal to negative 7, in order to get this y all by itself, I have to zero out the x's on this side. I have 5 x's, so I want to do the opposite of the positive 5x, and I'm going to subtract this 5x on both sides. Okay, I'm essentially wanting to zero out, get rid of all the 5 x's on this side to leave just that y, so that we have y equals. Now, because these two are not like terms, this is just going to stay negative 5x minus 7. And so now that top equation, these two are the same equation. We've just manipulated it to where y is equal to negative 5x minus 7. And so now I'm going to take what y is equal to and plug it in for y in the other equation. And when I do that, I want to make sure I put parentheses around it. So I'm going to rewrite this top equation knowing that y is equal to negative 5x minus 7. So now I've essentially combined both equations into one equation with just one variable, my x. And because I have an equation with one variable, I can solve this equation for x. So I'm first going to distribute this negative 4. So we'd have 6x plus 20x plus 28 is equal to negative 24. I'm going to combine my like terms. So we have 26x plus 28 is equal to negative 24. Got to isolate this 26, so I'm going to subtract 28 on both sides. Negative 24 minus 28 is going to give us negative 52, my 26x. Then we have to divide by 26 on both sides. So x is going to be equal to negative 2. So we found our x for this equation. Now we just need to find our corresponding y. And in order to do that, I'm going to take what our x value is equal to and plug it in for x into that equation we manipulated before. So we have y is equal to negative 5 times negative 2 minus 7. So y is equal to 10 minus 7, and y is equal to 3. So our final answer, because x is negative 2 and y is 3, is going to be negative 2, 3. And that's how we'd solve by substitution. Sometimes we may be given the equation where we have y is equal or x is equal to something, and we can just plug in from there. But other times we're probably going to have to manipulate, and that involves either subtracting or adding out the other variable. And then if I had something in front of this y, I'd have to divide that out as well. Like if I went this way, I'd have to divide negative 4 into negative 6 and negative 24. Okay. So our next example is going to be solve by elimination. And the key for this one is we want opposite variables that cancel each other out. So if we look at our equation, I've got 9x plus 2y is equal to negative 9, and then negative 9x minus y is equal to 18. So opposite variables are going to be variables with coefficients on opposite sides of the number line. So if I think about a number line, all right, the number negative 3, opposite that on the number line would be positive 3. So looking at our equation, I have a positive 9x and a negative 9x, and that's what I want to be able to solve by elimination. Because what I'm going to do is essentially combine both of these by addition, where I'm going to add 9x plus negative 9x, 2y plus negative y, and then negative 9 plus 18. So I'm combining. What's going to happen here is 9x plus negative 9x becomes 0x. 2y plus negative y becomes just positive 1y. And then negative 9 plus 18 is going to be 9. And so what happens, because we have 0x here, that goes away, and this just becomes y is equal to 9. And looky there, our equation has solved itself. I already have 1y. I have y is equal to 9. So I'm going to take that y value and plug it in for a y value into either equation up top. Let's go ahead and pick this one. Okay, so I'm plugging that 9 in for y in my first equation. I could have done the second equation, but we're going to do the first equation here. So we have 9x plus 2 times 9 is equal to negative 9. This becomes 18 is equal to negative 9. I subtract my 18 on both sides. 9x is equal to negative 27. Divide by 9, divide by 9. X is equal to negative 3. So again, we have one solution here. It's going to be at the point negative 3, 9. So we'd have this case, if we were to graph this, we'd have two lines that intersect at this point. Okay, so it's pretty nice with elimination if we have opposite variables already. Well, they're going to cancel out right from the get-go, and then we're off to the races solving for our other variables. Okay, notice there's a trend with both of these. We solve for one variable, and then once we have one of the variables solved for, we plug it back into one of the original two equations or one of our manipulated equations to solve for the other. So let's look at another solve by elimination. Okay, again, I want opposite variables. Here I don't have any true opposites. I've got one positive, one negative, but if I were to combine them together, they wouldn't cancel each other out. They're not opposite each other on the number line. Here again, I've got a positive and a negative. They're not opposite each other on the number line. So I'm going to have to multiply one or both of my equations to where our coefficients become opposite of each other, truly opposite. So looking at these two right here, right? I want to think, is there a number I can multiply 3 to be positive 7, so that it's opposite this negative 7? Well, unfortunately, I don't have a number that I can multiply 3 by to make it positive 7. If I look at negative 7, there's nothing I can multiply negative 7 by to make it positive 3. So we're actually going to have to end up multiplying both of these equations in order to cancel out one of our variables. So we want to think, what can I multiply either of these numbers by? And I'm picking these numbers just because looking at those, multiplication probably gets a little bit tricky pretty quick. Okay, you could do it. You could multiply both of these numbers to see where they meet up at something they cancel out, but I don't have anything I can multiply 9 by to make it positive 21 and vice versa. Okay, so I'm sticking with these numbers. So I know that on our times table, 3 and 7 meet up at 21, where I can multiply 3 by positive 7 to make it positive 21, and I can multiply negative 7 by 3 to make it negative 21. Now notice, I put a parentheses around this whole equation on both of them. That's because I'm going to multiply this entire equation by 7 and this entire equation by 3. It's called scaling. I'm going to scale this equation by a factor of 3 or 7, and I'm going to scale this equation by a factor of 3. So after I multiply 7 out to each of the values in here, I'm going to have 21x plus 63y is equal to negative 21. And then I multiply 3 out by all the values in here, and that's going to become negative 21x minus 63y is equal to 21. Now you may be noticing something here, okay, but because now on my variables here I have opposite values, I'm going to go ahead and look to add both of my equations together. 21x plus negative 21x is going to give me 0x. 63y plus negative 63y is going to give us 0y. And negative 21 plus 21 gives us 0. So I have 0 on the right-hand side. And because 0 times x is 0 and 0 times y is 0, 0 plus 0 would give us 0. Notice both of our variables got eliminated. And we're left with 0 is equal to 0. And that's a balanced equation that we know is true. So this is one of our special cases where if we eliminate or we substitute and our variables go away and we're left with a balanced statement, either 0 is equal to 0 or some value number is equal to itself. This is where we have infinite solutions. Okay, infinite solutions in this case where we cancel out. If all of our variables canceled out and maybe we were left with, let's talk about a hypothetical world over here. Let's say everything canceled out and we were left with like 0 is equal to 3. Well, we know 0 is not equal to 3, so that would be no solutions. Again, this means that these two end up being the same line when graphed. This would mean that the two lines are parallel to each other and never intersect. All right, last example in this video is going to be solved by graphing. So I have y is equal to negative 1 over 2x plus 2, and then negative 2x plus 3y is equal to 27. And we're going to get a bit of a review of graphing slope-intercept equations, as well as going from standard form to slope-intercept. Okay, so remember slope-intercept, y equals mx plus b. That b tells us where to begin on the y-axis. The m tells us how to move to the next point. So I'm going to graph this first equation in blue. And because I have y is equal to negative 1 over 2x plus 2, well, 2 is in place of the b, so I'm going to start at 0, 2 on my y-axis. And then our slope is negative 1 over 2, so because our slope is negative 1 over 2, that means I'm going to go down 1, right 1. So from that point, I go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. And then once I run out of space, if I want to continue making my line more clear, I can go back to where I started, and instead of going down 1, right 2, sorry, was I saying down 1, right 1, down 1, right 2, down 1, right 2, I'm going to go up 1, left 2. Complete 180 here. Up 1, left 2. Up 1, left 2. Up 1, left 2. Here I'm going to sketch my line. Maybe not the best, but I have these points to help me see what points are on that line. And then I'm going to look at our second equation. Well, our second equation is in standard form, not slope-intercept form. So I'm going to have to rewrite this in slope-intercept form, much like I did with substitution where I have to isolate the y. So I'm going to add 2x to both sides because I'm looking to get rid of that, or get that y by itself. And again, these are not like terms, so I can't combine them. And then I have to divide by 3 from that y, and when I do division, I have to make sure I do it to everyone. So here I'm going to start at 0, 9 on my y-axis, and my slope is going to be 2 over 3, so that means I'm going to go up 2, right 3. Well, that would have me go off the page. So instead of going up to right 3, I'm going to go down to left 3. There we go. And then I'll sketch my line. And I see that my two lines intersect at this point right here. So that point is at 1, 2, 3, 4, 5, negative 6. 1, 2, 3, 4, 5. So our solution is negative 6, 5. Hopefully this was a good review, and I'll see you all in the next one.